Hello everyone, welcome to Astronomy on Tap. I just want to make another announcement. If you want to participate in trivia, we're going to get started momentarily, and please come get a trivia sheet and golf pencil from either Binh or Sam if you have not gotten one already and you want to participate in trivia. Okay, hello everyone. So we're going to get started, but once again, if you did not get a trivia sheet and you want to play, we do have them up at the front here, so you can come grab one right now. So welcome to Astronomy on Tap, January. It is my pleasure to be here once again, and there's a food truck, and I believe the food truck will be here at most of the Astronomy on Taps for the foreseeable future, which is great. So tonight we have two really fantastic speakers. I like them both a lot. The first talk will be on if light can't escape black holes, how do we see them? And the second talk is titled Four Kingdoms, One Sky. So of course, before we get to the talks, we will do our usual trivia session. And so just in case this is your first time, I'll explain. I will put every trivia question up on the screen for 30 seconds apiece, so you can write your answer down. At the end, I will go back through and show you all the questions for a second time, but only for 15 seconds apiece on the second time. And then we will collect your trivia sheets and grade them during the first talk. In the intermission, I will announce the trivia answers and the trivia winners. And then after the second talk is over, if you won trivia, you can come get a prize. Okay, is everybody ready? Great. Is this echo? Can you hear this echo a lot? Do I need to deal with it again? No? It's fine? Okay, great. Fantastic. So with that, first round through the trivia questions. Here we go. Oh, this is great. I muted. Am I muted? Okay, I'm muted now. Okay, cool. Oh. David says he knows. Okay, so at this point, if you have all of your answers down, it's time to turn in your trivia sheets to either Sam or Binh, who is also our Astronomy on Tap speaker, but is also a trivia master. Yes, and please bring the golf pencils too.
You spilled my
You can
beer
just give
onto
it
my
to
laptop.
I can grade them so you can focus. Okay. All right. All right, so if all of the trivia sheets have been turned in at this time, it is my pleasure to introduce your first Astronomy on Tap speaker of the evening. David Wang will be speaking. The title of his talk is If Light Can't Escape Black Holes, How Do We See Them? David is a graduate student at the University of Washington's Astronomy Department. Woo! He studies X-ray binaries, which are star systems with two objects, one of which being a neutron star or a black hole. And David is also interested in observing transient phenomena or very rare events happening in space, which I'm sure he'll tell us maybe lots about, or maybe not tonight in his talk. So with that, it is my pleasure to introduce David.
Thanks.
And he's really good at making sourdough, by the way. It's actually that.
Thanks, Megan. You can all hear me? Yeah. All right, well, I'm David. I'll be talking about how we can find black holes if nothing can escape. But actually, if you've seen Interstellar, you know that there actually is a force that transcends all dimensions and time. That, of course, is love. Actually, when I was an undergrad, this movie came out, and our school arranged like a viewing session, and then Kip Thorne did a Q&A afterwards. And everybody asked him all these like science of interstellar questions, and he responded to all of them going, well, if you buy my book, The Science of Interstellar, you'll find that blah, 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 blah. But at the end, this other guy from my dorm walked up and was like, Kip, what do you think of the fact that love is the force that transcends all dimensions? And I think his literal words were, we had to throw a bone to the audience. So if we're not going to find black holes with the power of love, this is what I'll be talking about tonight. So I'll go over a little bit of background, sort of like how astronomers think about black holes, important stuff to know. And then I'll talk about how black holes actually suck up material. And then finally, I'll talk about how we find black holes that are in our galaxy, and then some other methods for finding black holes that you might hear about in the near and mid-future. So first off, some basics. So Black holes are these objects where the escape velocity from the surface or past the, there's really no surface, but there's this event horizon. Past the event horizon, the escape velocity is greater than the speed of light. So nothing can escape, even light. And there are sort of three flavors of black holes that astronomers talk about. So there are stellar mass black holes. So these are generally between 3 and about 100 solar masses. Astronomers measure mass relative to the mass of the sun. So a solar mass is exactly what it sounds like, 1 times the mass of the sun. On the other end of the scale, we have supermassive black holes. So these are greater than 100,000 solar masses. So a lot more massive than stellar mass black holes. And these are usually found at the centers of galaxies. And in between these two types of black holes, we have intermediate mass black holes. And we don't know a lot about these. We have very few examples, and I will not be talking a lot about these. Just a couple more details. So because stellar mass black holes form from supernovae, so basically the collapse of stars that are greater than 8 solar masses, they're kind of found wherever you would see stars, like throughout our Milky Way galaxy. In fact, it's thought that there are like 100 million of these just floating around our galaxy. I'll explain why that's not a problem later on. But yeah. Then we have also supermassive black holes. So these were likely formed when the universe was younger and denser, and it's still a bit of an open question how these things came to be. But they formed in an environment that was very different than what we see today. And again, there's only like a couple examples of intermediate mass black holes, and they're all from the mergers of like stellar mass black holes. So I will be focusing on stellar mass black holes because those are the ones that are sort of around us in our vicinity, and they also happen to be the ones that I study in my research. And here's this like sort of cartoon diagram of a black hole. And I've labeled a couple of important things here. So first off is the accretion disk. So we have this gas that's orbiting the black hole. The black hole is here in the center. You can't see it, but it's there. And this gas is slowly spiraling in. Really, it's actually mostly just orbiting and not going in. We have the black hole shadow. So anywhere that's bright here, you can see, because like in theory, photons would be coming off of this and like hitting your eyes or your detector. But where you don't see any brightness, that's where like photons can't make it to you. So this region here is called the black hole shadow. So no photons are detectable from that region. This specific cartoon has like the relativistic effects. So you can see sort of the far side of the disk and the underside of the disk. So that's because light is being bent over it. I won't also go too much into that, but just wanted to show that here in case you were familiar with this visualization. And then finally, there's a corona that's also not really depicted here, but that's this diffuse, very, very hot gas that's sort of in this cloud above and below the accretion disk. And for the rest of the talk, I'm going to focus on the accretion disk itself. This is sort of where a lot of interesting physics is happening. We're not getting photons from the black hole or the black hole shadow, but we are getting lots of photons from the accretion disk. And so while we might not be able to detect the black hole itself via photons, we can definitely learn about them from the light coming from accretion disks. Okay, so this is the most important slide of this presentation. If you get one thing from my talk, I want it to be this. And that's, it's actually really, really hard to get stuff to fall into a black hole. So we have this idea that black holes kind of move around sucking whatever is in its path. But unless you pass like extremely close to a black hole kind of just affects you the same as any other object that mass would. So for example, if you replace the sun with a black hole of equal mass, I mean, some terrible stuff would happen, but the Earth would continue orbiting the mass in the center of the solar system. And in the same way that the Earth and the other planets don't just like fall into the sun, in the same way stuff orbiting a black hole doesn't just fall in. There's this pesky thing called angular momentum, which prevents that from happening. So instead, all that matter forms what's called an accretion disk, which is the stuff that's around the black hole. And in this video, we're zooming in, and you can see different components of the disk. You can see some jets. We're going to cut away so we can see a little bit of the inside, and here's the black hole. And so I'm just going to take a still from that video and talk a little bit more about what's going on in this picture. So first, we have this blue region that's fairly close to the black hole. So the gas here is very, very hot, and it's so hot that it's emitting photons that are very high energy in the X-ray part of the electromagnetic spectrum. Out further in the disk, the material is much cooler, and so the photons coming out are proportionally less energetic. So we would probably see this area in visible light or in the optical portion of the spectrum. And then finally, we see these jets that are coming out. So this is material that's being accelerated perpendicular to the disk by the black hole. It's not exactly clear the physical mechanism that causes this, but this stuff is being accelerated incredibly quickly and is highly energetic. I think the easiest way to detect this is with a radio telescope. So a lot of this emission is in the radio part of the EM spectrum. So when you have a black hole, you get all these kinds of emission, and that can help us try to detect these objects. And so here for the fanciest graphic of my presentation, we have a system here now. So we have the black hole in the center. And in order for an accretion disk to really be interesting, it needs to be like supplied somehow. So the easiest way for that to happen is to have a star that's orbiting the black hole and actually transferring mass into the accretion disk. So these binary black hole systems are very important, and spoiler alert, all of the black holes we know about in the galaxy are in these binary systems. So in this sort of picture, we have this mass that's being transferred into the disk here. And mass, there's some amount of mass that's going on in the black hole, but most of it is staying in this accretion disk right here, because there's nothing to cause the material to lose angular momentum. You need something like friction or viscosity in the disk to cause it to spiral in. So right now, most of the mass is just hanging out here. And maybe you can see by the thickness that I've drawn the arrows that this mass transfer rate from the star doesn't necessarily have to be the same as the mass transfer onto the black hole. In fact, it's probably greater here than it is here at the moment. And as a result, stuff builds up in the disk until you reach a critical density. And at that point, the disk, which is mostly made of hydrogen, this material coming off the star, ionizes, and that causes this like runaway process where the whole disk can ionize. And at this point, you have all these charged particles floating around, and you have this effect called the magneto-rotational instability that provides that viscosity, that sort of friction that allows the mass transfer rate to increase by a lot. I will not be taking questions about the magneto-rotational instability. Yeah, so now the mass transfer rate is much greater into the black hole. All that stuff is, you need to get rid of that energy somehow. Not all of it is going into the black hole. Some of it is being accelerated outwards. Black holes are actually very efficient at converting this material into energy. There's something like 6 to 40% efficient. And so if we use like E equals m squared, we can find that the energy that's produced is incredibly high, even for like a pretty moderate mass transfer rate. And so a lot of this light is being emitted as these soft X-rays. So soft is maybe a little bit of a misnomer here because they're still very energetic. But we have these very high energy photons that are coming up off this disk. And of course, we get other emission at other wavelengths too, but that X-ray radiation is really important. So there are like tens of confirmed and candidate black holes in our galaxy. All the ones shown here are in these binary black hole systems. So this plot is just showing the number that we know as a function of year. So we first started finding these things in 1970. This kind of corresponds to when we launched the instruments that will detect these, and that's kind of grown sort of linearly. The difference between the red and the blue bars here is that the blue ones are confirmed by dynamical observations, which basically means that they looked at the orbital period of the star going around and were able to suss out like how much mass this central object has. So that's like confirmed, but based on the behavior, it's likely that most of these are black hole systems. All right, so we've sort of described the mechanism for getting an outburst here. So how do we actually detect this? So here's a picture of the Milky Way, or of the sky, that's sort of been projected onto this rectangle. And so we have the Milky Way running down the center here, and the locations of all these confirmed black hole binary systems plotted. You can see that they're not distributed evenly throughout the entire sky. They're mostly located in this galactic plane right here. And there's a lot of stuff that's going on in the plane. So you see like this bright stuff, this stark like gas dust lanes. Lots of stuff is emitting or absorbing in visible or optical wavelengths. So instead, we could look at the same sky, but in X-ray. So back here, we were looking at using detectors sensitive to visible light photons. Here, we're sensitive only to the high energy X-ray photons. This was taken by MAXI, which is, I think it's like an experiment aboard the ISS. You have to be above the atmosphere to detect X-rays. And you can see it's much less busy, and you have all these like point sources here. Some of them are circled. So for example, Cygnus X1, GRS 1915, these are binary X-ray systems. So that X-ray radiation coming off is much higher contrast with the rest of the sky. So it turns out most of these systems are actually discovered using X-ray telescopes because of this. If they go into outburst and their X-ray brightness suddenly increases, they might become sensitive enough for this mission or some other X-ray mission to detect. So this plot is kind of complicated, so I'll walk you through this slowly, but this is a plot that I've made from my research. And this shows one outburst from an X-ray binary. So since these things are discovered in X-ray, they're generally called X-ray binaries. And on the x-axis here is time. So this scale spans roughly like 150 days down here. So the outburst itself lasts maybe like 80 to 100 days. And on the y-axis on the right, this is the X-ray count rate. And at quiescence, or at the sort of low non-outburst level, it's sort of around here. And the black points show the X-ray emission. So at the high bright state, outburst state, sort of up here. And what we see is roughly like 100 times increase in the number of X-ray photons we detect from this source during outburst, and that's enough to trigger the X-ray telescope. I've also plotted visible light observations. So this was taken with a telescope that's actually pretty small. It's like a 1.2 meter telescope. And in visible light, we have those points plotted in both pink here and in green. The different colors just represent different parts of the visible light spectrum, something like 650 and 550 nanometers or something. And the visible light brightness scale is on the left-hand side right here. And if you've ever done any sort of like amateur astronomy or worked with astronomical data, this scale makes like absolutely no sense. But basically, this increase is about 20 times in brightness. So going from magnitude 19, which is dim, to like magnitude 16 and a half, which is bright. And so I'm going to take a quick slide to plug my own research, which is that although we find most of these objects in the X-ray, we have more optical instruments, and we specifically have some instruments that are designed to look in the same place repeatedly at pretty high interval or pretty high cadence, as you would say for an astronomer. And so if we look for these big increases in brightness, say something like here, that happens in a roughly, a very short amount of time. This is maybe 1 to 2 weeks. This means something very explosive is going on here and could be worth following up with, say, an X-ray telescope. And the reason why we might try to look for these using visible light is that that light is coming more from the accretion disk rather than stuff very close to the black hole. So you can get sort of some data from a different part of the system. Also, sometimes the X-ray signal is not quite enough to trigger your X-ray telescope, and there are many more visible light telescopes that are more sensitive. And so for this specific system, it persisted for almost 150 days. Unfortunately, it's pretty faint in the X-ray, and we weren't able to get a good spectrum of it, so we're not sure what this is. If that thing that the normal star was orbiting was a black hole, a neutron star, or a white dwarf, but this is some sort of binary system where there's accretion going on. All right. So for the last couple of minutes, I'm going to talk a little about other methods for observing black holes. This is not my research, but it's also very interesting, and a lot of these are very recent missions or upcoming missions that you might want to keep an eye out for. So one way that you could detect black holes is via tidal disruption. So like we were saying earlier, it's really hard to get stuff to fall into a black hole. You have to get really, really close. And that's why even though there's 100 million black holes in the galaxy, it's very unlikely that we pass close enough to have something really bad happen. But in the case where you do pass close enough, your star or whatever object can get torn apart by the tidal forces of the black hole. So that's what's going on in this specific animation here. And when this happens, this releases a lot of energy, and this is also detectable out to really far distances. So we can find these in other galaxies. And again, this is another reason why you shouldn't be worried about this happening to us, because if this happened a lot, we would see them in our galaxy a lot, but normally we see these in very far away galaxies. But what does detecting one of these look like? Hopefully this light curve is visible. But again, we have time on the x-axis here, and magnitude or brightness on the y-axis here. And this is an event taking place over 150 days. It kind of appears out of nowhere. There's a little bit of a rise where this thing is first getting torn apart, and as the material sort of spreads out, it cools and gets dimmer. And so on the right, I have the actual image that this thing was in. So can anybody spot the black hole? Oh, it's right there in the middle. I don't know if that's super visible, but yeah. So again, this is a plug for these big optical surveys. This was found using a visible light telescope, and the telescope was taking data every 2 days. So they noticed that this thing was suddenly here one day, and then it got brighter, and then it's getting dimmer. Another way that you can find black holes is via microlensing. So this is where the gravitational effect of an object, sometimes a star, sometimes a planet, and it can be a black hole, bends the light of a background star and sort of amplifies it. So normally you're only getting light from this background star if it's going directly to you. But now if this is in just the right place, the light from like this outside is also going towards you. So the brightness increases a lot when the orientation is like just right. And you can look for this characteristic microlensing increase in brightness. So the shape of this curve can also help determine the mass of the object. So I can tell you if it's a star or a planet or a black hole that is causing the bending of the light. So there's a telescope launching, a space telescope, the Nancy Grace Roman Space Telescope, launching in 2027. And one of its goals is to conduct a microlensing survey of our galaxy. So this is sort of the best way to discover those free-floating black holes that don't have a companion to transfer that mass and form an accretion disk. Actually, there was one microlensing candidate, I think that was published last year in our galaxy, and they took, I want to say this is about a year on the bottom here. These are in days. And this background star got way brighter due to something lensing it. You can see this microlensing curve, and then it faded. And zooming in on the week of maximum brightness, it looks like the data fits the model very well. So it's pretty likely, actually, that this is a free-floating black hole. So maybe I lied a little when I said that all the black holes we knew about in our galaxy were in binary systems. But there's no way to confirm that this is a black hole because the event only happens once. So once it's over, that black hole is gone forever. All right, the final way I'm going to talk about for finding black holes is via gravitational waves. So this is not even with like electromagnetic radiation. We're not detecting photons here. Instead, we're detecting these ripples in space-time that are caused by these like very massive compact objects moving close to one another. And like we said in the trivia, there's a detector that's pretty close by to us, LIGO. And it's designed to look for these like small changes in space-time that are caused when two black holes orbiting each other get very close and merge. And so LIGO and Virgo, these gravitational wave observatories, have detected hundreds of black hole mergers. If you're more interested in those, I would encourage you actually to go out to the LIGO site in Hanford, Washington. It's really informative. They give public tours, and they can explain it a whole lot better than I can. All right. So thanks for listening, and I'll take any questions. Oh, wow. Right there.
Does the angle of the accretion disk relative to the Earth impact the information you get from it?
Yeah, so the question was, does the angle of the accretion disk relative to Earth impact the information that you get? The answer is yes, it definitely does. This is not quite my area, but I know that if you're trying to confirm the like mass of the central object, then depending on your inclination angle, you'll get a better measurement of the central mass or not, and you'll see more variation or less variation in the signal from the orbit, like precessing, for example. I mean, the back and the Seahawks beanie, yeah.
So if the accretion disk has a lot of orbiting hydrogen, are there stars forming in the accretion disk?
All right, so the question was, the accretion disk has a lot of orbiting hydrogen. Are there stars forming in the accretion disk? So the short answer is no. Maybe the longer answer is that there's probably not enough hydrogen. Well, first off, there's not enough hydrogen in the accretion disk to form stars. But more importantly, in order to form a star, you need the material to become very, very dense, and that density is what causes the fusion to begin. So usually you actually need the material to form a star to start out very cold, so that so that it doesn't just like evaporate away when it compresses. Hope that made sense. Here in the front.
I think one of your earlier slides you showed just a little title of corona, about 1 billion degrees. What does that corona consist of?
Yeah, so I showed the corona, but then I kind of didn't talk about it. So the corona is made out of very hot gas. It's made most likely hydrogen, and it's like 1 billion degrees, so it can also emit X-rays. And I think the corona is going to be around whether it's in the outburst or the quiescent state. So there's some sort of X-ray radiation coming off the system either way.
It's not part of the accretion disk.
No, so it's going to be really, really hot. So it'll be very difficult to get stuff that's that hot to go anywhere, because it's the like particles, the gas particles are traveling very quickly. Yeah. Maybe in the back there.
You speak of an accretion disk rather than an accretion sphere. Why is that?
Yeah, so that's a good question. So we might intuitively think about stuff falling into something as being spherical. So why does the material form a disk instead? So the answer again is due to conservation of angular momentum. So there's going to be some sort of net spin to the stuff that's going towards the black hole. And so the like gas or stuff that's falling in, as it gets closer, it's going to start orbiting in some orientation. And when that happens, the spinning, there's like a centrifugal force you can think about that's pushing outwards. But you still have that inward attraction to the center. And so eventually you'll have only outwards pushing in one direction, but you'll have that inward pull in all directions. So that's why it forms a disk. The disk is formed in the plane where of the like angular momentum vector. It's like the physics way, but it's like that's the direction that stuff is getting pushed outwards centrifugally, but everything else is getting pulled towards the disk gravitationally. Does that make sense? Okay.
Yeah, and so that's sort of similar to why our solar system and galaxy matter are also flat.
Yes, so our solar system is all in one plane, and the reason for that also is that the stuff that it formed out of also created an accretion disk at the beginning of the solar system, we think. So yeah. One more question. Maybe here in the front.
Sure. So it seems like black holes just kind of destroy a bunch of stuff, eat a bunch of stuff. How much of the universe is black holes compared to non-black holes? Do we know that?
That is an interesting question. So off the top of my head, I don't know that. But other people have thought about this. And back when people were trying to figure out what dark matter was, some people thought that dark matter could be like primarily black holes, and we don't see them because they don't emit light. I think that's been mostly debunked, or that's been like basically debunked. The universe is probably not mostly black holes, but I don't know what the specific proportion is. That's all the questions, but if you have other questions, I can take them maybe afterwards. Thanks.
Great. Okay, sorry. So now we're going to announce the we had a 5-way tie for second with 7 questions right. I feel like just 2 prizes is not enough prizes, but unfortunately 7 prizes might be too many for this episode. So I will give everybody honorable mentions, and then maybe we'll have 2 of our second place people picked at random, if that sounds like a good plan. Okay, before I announce the winners, I will give you the answer to the question. So here we go. Question 1. It is false that the first image of a black hole was published during COVID-19. None of the above is the answer to taking this black hole image requires an international network of telescopes. The accretion disk, as David alluded to in his talk, is the flow of material that loses energy and slowly falls onto a black hole. I can't pronounce their names, I'm sorry. Reinhard and Andrea won the Nobel Prize for discovering the black hole at the center of our galaxy. In 2015, gravitational waves emitted by emerging black holes were detected in Benton, Washington. South Korea has the oldest surviving astronomical observatory in Asia. The supernova of 1054 was recorded during the Song Dynasty. This is an armillary sphere. Armillary sphere. Sorry, I'm so sorry. Okay, it is true that medieval East Asian astronomers used pots of black ink to indirectly look at sunspots. And this 1490 map of Hanoi has a place called the Office of Administering the Heavens. It is an astronomical and meteorological observatory. Okay, so with that, thank you. Our first winner with 8 right is Aliens. Oh, that's funny, like aliens. Okay. Our second first place winner with 8 correct is Singularity. Well done. Okay, and then our honorable mentions are Zachariah and Colleen. Basil. Fantastic. I'm sorry, I can't really read the handwriting, but Black Sail Shoal? Does that ring a bell to me? Okay. Simcoe's Peeps. We're all Simcoe's Peeps, I would argue. And Skycar. Okay, so now Sam is going to come and select 2 trivia tickets at random. Everybody, welcome Sam. Sam does all of the social media posts for Astronomy on Tap, so you can thank her for that as well. So go ahead and pick 2. Okay, and 2. Okay. So, in addition to their honorable mentions, Basil and Black Sail Shoal will also be getting prizes. Okay, so now we're going to take like a 5 to 10 minute break so everybody can either go get tacos or go get beer or go to the bathroom, and then we will come back with Binh Nguyen, our second speaker of the evening. Thank you.
The reverb really makes it sound much more natural.
Oh, really? Okay, that's great. Good job, David. That was so good. I really liked that a lot. Also, the interstellar joke at the beginning was really funny.
I think you really enjoyed that one.
know the black hole stuff too. To quote Eric, I will not be taking questions. Did you have Tom's review on Tom's?
Well, you're gonna dip to the table.
It's on. It's on.
Okay, everyone, welcome back. I hope you got both tacos and beer. Yes. So at this time, it is my pleasure to introduce our second and final speaker of the evening. Binh Nguyen is also a PhD student in astronomy at the University of Washington. They study galaxy evolution through cosmological simulations, and they're also interested in astronomical observations and the surviving records of medieval East Asia. In addition to that, Binh is a published poet and author, and I'm hoping that they will elaborate on that, hopefully, during their talk. Okay, so with that, it is my pleasure to introduce Binh.
Oh no, I'm kind of short. Can you hear me? Wait, how do you do it? Yeah. Okay, awesome.
You can adjust it.
Okay, awesome. Hey, so my name is Bing, and as as I have been introduced, that's who I am. And and because this topic is a little bit different from what David did or what most people did, so I want to have like an intro kind of thing to like kind of lead you into it, to familiarize you. So okay, let's start. So the year was 1928 in California. Can you see? Yeah. So 1928, California. It was like the Roaring Twenties and whatever. I don't really care about the setting. Let's just go into it. So 1928, Edwin Hubble was an American astronomer working here on Mount Wilson. And what he was doing was that he was observing the Crab Nebula. And the Crab Nebula, for those of you who don't know, is like this thing in I forgot, it's Taurus. And it's a nebula where people have been like looking at for a while, and they saw that, oh, this like cloudy kind of thing has been expanding. And so Edwin Hubble looked at that himself and was like, oh yeah, that's expanding. And later he sat down, he actually calculated the rate of expansion of the Crab Nebula. And he found something interesting. He found that if he assumed that like the Crab Nebula expanded at the same rate over the course of his lifetime, he could trace it back to an event 900 years before him. This is what he said. He basically said that to be able to achieve this size with that rate of expansion, the Crab Nebula must have formed around 900 years before Hubble, and that coincided with a record in the Chinese historical documents of a sudden bright star, and he suspected that that star was what like caused the Crab Nebula. And later on in this paper, he suspected like maybe like this star like exploded or something. Didn't really know. And years down the line, that was proven to be true, and that the Crab Nebula was confirmed to be the first ever like supernova remnant that humans know about. And interestingly enough, like the reason why Hubble could come to that conclusion was through looking at the Chinese records. He said it right there. So that brings us to this question: what else do those Chinese records have? Like, like how valuable can they be to astronomy and to our modern understanding of like celestial science? And that is my question for today. And I'm gonna lead you down like into like an overview kind of thing, but that's what my talk is gonna be. It's called Four Kingdoms, One Sky. Yeah. And yeah, so that's the main topic of today. I'm gonna tell you like an overview of like medieval East Asian astronomy, and it's gonna be like, this is a topic that doesn't really have an ending to. It's not like something with a question and an answer like specifically, but I'm gonna try my best to introduce y'all. Okay, now, what does all of this mean? Like, I'm talking about like East Asian records, but what exactly is East Asia? So in geography, East Asia is like the part that's east of Asia. But in history and in basically social science and humanities, the East Asian cultural sphere actually refers to 4 different countries. China, Japan, Korea, and Vietnam. I mean, well, Korea here includes both South and North Korea, but let's just say that, and China has China and Taiwan, but it's modern stuff. Let's just stick to this, okay? Anyway, so these four countries have something in common, which is that they have like they have some shared traditions for sure. Like their system of beliefs is basically like a synchronization of what is it? Confucianism, Taoism, and Buddhism, and then they interact with each other. And basically, the relationship between these countries is that China was like the original one, the OG, and then later like they brought their culture to other places either through contact or through conquest, as with Vietnam, and then it just stayed there for a while. It became the foundations of these countries. So we usually call this like, for example, you would say like Chinese New Year or something, but like the proper term would be like Lunar New Year, and that's why we're calling it like the East Asian culture sphere to be like inclusive. But anyway, what does this have to do with astronomy? Well, see, all of these cultures, they had a great interest in astronomy, which in their language, like in classical Chinese, which is a language that they all used, means the study of the patterns of the sky or heavenly patterns or whatever. And they believed in this like ever-changing universe where like changes in the sky, changes you see in the sky, either reflect or predict what can happen on Earth. And these like kingdoms, these cultures are centralized around an emperor who rules by the modern, like what modern like historians call the mandate of heaven. And because of that, you know, dude is literally like told by heaven to govern. So all of these celestial stuff, like they are basically like omens for the emperor. So a lot of these like astronomical phenomena are recorded in order to tell the emperor that, hey, like maybe heaven doesn't like what you're doing, whatever. And that means that like not only do this culture have like a very like obsessed kind of focus on astronomy, but it's also like a top-down kind of thing because like you have to look at this for the emperor. And as a result, like East Asian kingdoms usually like have their own bureaus of astronomy. In different countries, they're called by different names, but I'm just gonna call them bureaus of astronomy. And they're responsible for timekeeping, making calendars, and observations. And observations include both like space, like you know, celestial observations like astronomy, but also meteorological. So that's why there wasn't to answer like a question in the quiz that had like meteorological observatory. And this bureau staff, those people, they would have to report directly to the emperor. And they're like astronomers in these kingdoms were part of the royal court, and so they are ranked. And in most of those kingdoms, like your rank determines the color of your uniform, basically. So if you can go back into the records and see what kind of color what kind of fabric this ranks used to have, you could actually like tell how astronomers were dressed when they went to work back in the day. And so this is like a reenactment of like somebody in the Nguyen dynasty if they were an astronomer, because their clothes would be like that and with that collar and all that, but though probably not as young and not as like attractive, maybe like old like bureaucrats, whatever. But yeah, that's my point. Anyway, so this is a very important job. It was a very important job for them. And the astronomers, they couldn't bring their documents home. And between these countries, they had like a trade system, but they didn't really trade the techniques of how to make a calendar or how to basically like make like, I don't know, instruments basically. And a lot of the times, like some countries have to come up with like inventive ways to get ahead. And so there's like a story combined from the Chinese and Vietnamese records of like this guy, like in 1301, like the Chinese records was like, okay, this guy, this Vietnamese envoy, he came to our country and he like smuggled some forbidden books out of our country. And then it was like they were like, please send blame to show righteousness. That's what they said. And then conveniently enough, like 30 years later, his son invented a whole new calendar system for Vietnam. And he became like his son became the head of the Bureau of Astronomy. So, I wonder what happened in those 30 years. And that's my meme of that. Yeah. Anyway, I hope you appreciate that meme. And but as for, generally speaking, these countries, like they all like maybe like the levels of development were not the same, but they managed to have something, some technology, some stuff in common for them to do astronomy. And so equipment. So, of course they got their eyes, most trusted telescope, I guess. Not really a telescope, whatever. But they usually build like tall platforms to stand up there and observe. And then they got like some, and for example, like this is a map of the Vietnamese capital in 1490. And how do you point this? I don't really know, but like that. Do you see the green thingy over there? Yeah, that's where. How do you
The green line button.
the green
Should
white?
be a button on the front with the green on it.
I can't. Sorry about that. Yeah.
This one
Oh,
is the laser pointer.
yeah, and that is where the Bureau of Astronomy is. In the quiz, it's called, I translated it literally as the Office of Administering the Heavens, but basically it's a Bureau of Astronomy. And they also have some other tech as well, like they have pots of black ink, like how Chinese ink is like completely black, and they have those things like that kind of liquid in pots to avoid looking directly at the sun. And they were able to like draw, like not draw, but like note like some sunspots thanks to that. And they also got their like systems of like stars / planets to do like comparison. For example, there was like a Chinese astronomer in the Han Dynasty who was like, if a star like the standard colors for stars are like white like Sirius, red like Betelgeuse, or something like that. But using their own name for those things. But they usually compare, for example, there was like a supernova in Korean records that was compared to Jupiter. So they literally compared brightness and all that. And it's their own comparative system. And they got a sundial, of course. And then there's something called an armillary sphere, which we don't really use anymore. But fun fact, an armillary sphere is on the flag of Portugal. Yeah, yeah. Now you're not gonna look at the Portuguese flag like normally anymore. And an armillary sphere is basically like a representation of like the sky with like the Earth like assumed to be at the center, and those things are like latitudes and longitudes and that kind of stuff. So it's not like there is an armillary sphere and then there is a celestial globe. The celestial globe is like a globe but has stars on it. But this is like to keep track of the locations of the stars, if that makes sense. It's like, minusculely different. And then they got something called rod calculus, which is really strange. And basically, it's their way of doing like calculations and equations. Like there were like books on how to represent polynomial equations using counting rods. And it can be a topic for another talk, but they were able to do a lot of inventive stuff with it instead of using like numerals like we do. Anyway, so that's all they got. And then what did they achieve? Well, they achieved quite a bit. So in the 5th century, there was a Chinese astronomer, I don't know how to pronounce his name, probably like Zhu Chongji or something. He calculated pi so accurately that like it was like the record for like a few hundred years until like an European like mathematician broke it in like the 15th century. So like from the 5th century to the 15th century, that was a lot of time. And then he also calculated Jupiter's orbital period to be like that, like 11.858 years. And the modern value that we know is 11.86, pretty accurate. And then there's another guy in Vietnam in the 14th century. His name was Trần Nguyên Đán, and he calculated like the coordinates of the planets and the stars for like thousands of years, basically, and he wrote it into a book. But we don't have the book anymore because presumably the book was burned with a lot of other books when China invaded Vietnam and was like, we're the only legit astronomers. You should be like subservient to us and something like that. It was like political stuff. And though we know that like this guy did all this because the contemporary people talked about it, they were like, yeah, this guy's a big deal. And other people were also big deals. And their reputation spread all over the world, especially with the Mongol Empire and other like, expansive empires that stretch like continentally. So in the 13th century, when the first ever like basically astronomical research institute was founded in Iran, like modern day Iran, it's in Marageh, Iran, in East Azerbaijan province. And basically the Persian astronomers hired Chinese astronomers to come and help them improve the Ptolemaic model. Of course, this model is like geocentric, so it's not correct anymore, but they made a lot of improvements, and that's like an image of the archaeological site of the observatory, as you can see right there. So what I'm trying to say through all of this like long like overview is that this was like a vibrant like field with different countries doing different things and having to resort to literally smuggling to get like some technology, but they were able to achieve a lot of the things that are very close to our modern scientific values and that kinds of stuff. And so let's dive into it, shall we? Let's just focus on a few cases. I have some cases today to show you. And so the first one, like I'm talking about like their observation stuff like that. Anyway, the first observation that I want to bring up is guest stars. It's a really mysterious term, right? But this was basically the word in medieval East Asian records to describe supernovae. Think about it. Supernovae, star-like things that appeared like suddenly and disappeared suddenly, like a guest. And guest stars. It's I mean, supernova, like nova means new. It's basically like, oh yeah, we haven't seen this before. It's new, so we're just gonna call them nova. And then, oh, they're also very bright, so supernova. It's like semantically, it's like the same thing. Gas stars and supernovae both denote like the newness, the strangeness of those phenomena. So yeah, it's not too irrelevant. Anyway, the guest star slash supernova I want to talk about is the supernova of 1054, the one that Hubble confirmed to be like the one that caused the Crab Nebula. So back to 1054. So this was the record made by the Song Dynasty. So basically, they were saying that like, oh, this should have appearance, but yeah, whatever. Anyway, they were saying that like in that month, in that year of that era, that they named era after kings basically, a guest star had appeared in the eastern direction under the watch of Tianguan. And Tianguan is a star that corresponds to Zeta Tauri in our modern like naming system. And those dates, and then it says like now it has disappeared. The negative entry was marked as April 6, 1056. And then the appearance, it was in July of 1054. So this was a guest star slash supernova that stayed in the night sky apparently for like 2 years. So it was a big deal, and many people were looking at it. So basically, from the records, we know that like earlier we saw that like the star first appeared in the early morning, and using like modern like the magnitude system, the thing that David was telling you, that like it's very weird. Like we could tell that like is it? It died? No. Sorry.
I'm so
Well,
sorry.
my microphone died like this star.
Sorry.
Anyway. Okay. Oh, well, never mind. Anyway, so from the records, and they say that like this guest star was like visible in the early morning, and modern astronomers have come back and kind of like converted that into like a magnitude, because like it has to be at this magnitude to be visible in the daylight, and based off of some other details. So the guest star, the supernova, was at like minus 18.1 magnitude. And if you look at the picture on that picture over there, you see it's in the middle, and it's like a simulation with stellarium basically. It looks like that. That's what the supernova would look like. Looks like. Sorry, and that's the moon. It's brighter than the full moon. That's how bright it was, and it became invisible like more like around like 650 days later after discovery. And astronomers have also tried to like convert that into like absolute visual magnitude, and it's like -7. So it stayed in the sky for a while as well, as the records showed. So what exactly was that? Well, the supernova like has a remnant, the Crab Nebula, and when you look at the Crab Nebula, like you're gonna find. I will explain that. You're gonna find a low abundance in nickel, and this is typical of a type of supernova known as type 2NP, where N stands for narrow emission lines. Because what happened was that the supernova, happened, and the light from that, like the star that became a supernova, already had like a circumstellar disk around it, and when the supernova happened, it ionized all of the material around it, and those materials like had like narrow emission lines, hence the N in the N right there. And it's a very rare thing as well. So like we don't really have this like a lot in our galaxy. That's why that's why it would have been great if these people had like spectrographs. That's why the meme is there. But with more research, they were able to like deduce. And funnily enough, fun fact, the guy that I got all of this info from, he was my professor. So yeah, weird flex, but whatever. Anyway, his name is Nathan Smith. He teaches at the University of Arizona. Anyway, it was the supernova was an electron capture supernova. What happened was that like the core of this star, like when it dies, like there was too much like oxygen and some other stuff in there, and those heavy elements, I guess, like the protons, like they took away some of the electrons that were supposed to be there to keep the star from collapsing, and so that's hence the term electron capture. And so with the electrons being captured, the star collapsed, and then it's supernova. And those supernovae usually have like a very high peak in brightness, which kind of explains why the one in on July 4th, like it was as bright, even brighter than the full moon, and it slowly like declined like that, like that, and then it plateaued over the course of 2 years, which is exactly what the records show. So you can see how like a combination of like ancient records, more like medieval records, and then like modern observations could help us understand what happened in the year of 1054 and maybe the universe in general, because this supernova, like I said, is pretty rare. Hence, I'm gonna bring them spectrographs. Anyway, and that's supernovae for those who are interested. Now, let's talk about something even more obvious. Comets. You probably have seen a comet, and they probably have seen a lot of comets. And there is an observation I want to focus on, which was in the early 12th century. Basically, this is what the record said. So in the Vietnamese records, it says that like, you know, spring, first month, a comet appeared in the west and its tail like streaking across the sky. That's impressive, but not like too many details. Well, here comes the Chinese records. They're like, yeah, this month, like this year, and then under this emperor, a comet came out of the west, and it was as big as the mouth of a cup, and its light spread out like stars. It was this long, it was this wide, it was just very detailed. And as you can see, like they try to use their like, you know, their terrestrial units of measurements to express the bigness of the comet. And astronomers have kind of tried to guess that as well, like, okay, what does this correspond to? And also there are some Chinese records as well, but I can't find can't find texts to show you. I just know that they exist because people talked about them. So I wish that Japan digitized more of their records. Anyway, so according to the Chinese records, the comets, like, yeah, people really converted those things into like degrees in the sky. So the comet's tail was like 90 degrees long and 30 degrees wide. And according to the Japanese records, we were not yet digitized, and the tail like just dwindles. Like the comet has a few tails, and it has like this tail that kind of dwindles in brightness. So if we go back to this with all of the descriptions of like, okay, it began from here and passed here and here, all that, you could kind of like see how the comet went. Let me show you. So it went from Andromeda down here. It went up to Aries, which is over there, and Pleiades and Taurus. So it went like that, and that's the north. That's north. So it went like that. But yeah, it was a very big comet, and you see like how detailed how many details you could have just from the records. And once again, I would love to show like more of the Japanese records, but like I'm just saying all these because I read them from the Japanese astronomers. I don't know where the records are. It's kind of sad to. I try to look, okay? I actually try to look. And yeah, that's me. That is me. But anyway, what was that comet? Well, it was one of the bright sun-grazing comets, the kind of comet that reaches the sun, like its perihelion, like the closest approach to the sun, was like 2 solar radii, so pretty close. Those like comets tend to get stripped apart, like if you saw like comet Shoemaker-Levy in 1992 or something, it's kind of like that, but it's like close to the sun, and it was ripped apart and became even like more comets. So a lot of astronomers nowadays, they think that like the comet that appeared in the records broke off into multiple pieces. It might have been the progenitor. Now this shouldn't have been plural, but progenitor of the comets of all of these years. So because you could kind of match its orbit with this comet's orbits. So yeah, it's pretty like compelling by combining both like modern stuff and also like medieval records. Now, that's a lot, you know. Now I want to wrap it up by bringing like maybe like a more limited case. So, blue sun. What the heck is that? Let's see. I would take like 1 or 2 guesses if you want to guess. You can raise your hands or whatever, or shout it out. Wait, that's a lot of. Wait, anybody? Can you raise your hand? Eclipse? Yeah. And you? I was also going to say eclipse. Okay, so people are saying eclipse, right? But the thing is that, like, these records have their own names for solar eclipses and lunar eclipses and partial eclipse and total eclipse. They can't just use a random ass word like blue sun to describe it. So let's check the records, shall we? This is a page from one of the last documents of Imperial Vietnam before it was like taken over by the French, and actually got this picture from the National Library of Vietnam. So they digitized it, not like Japan. Anyway. Anyway. So on that day, the sun was blue. Early in the morning, the color was blue, and then gradually turned white. Travelers had no shadows, and there was no light anytime throughout the day. What the heck was that? Oh, there's a guess. What is it?
Volcanic eruption.
What did you say?
Volcanic eruption.
Okay, any more guesses? Well, anyway, so the day was that in 1883. So does anybody know what happened in the year 1883? Exactly. Yeah, so you were right. It was a volcanic eruption of Krakatoa, like probably one of the most powerful volcanic eruptions ever recorded. And I found this picture. I didn't even know they could stay so close and take pictures of that. But the volcano erupted, and it sent shock waves traveling around like across the globe 3 times, the same shock wave. And like people all around this region in Singapore and all that, their sailors, their eardrums were blown, and all of a sudden, and like a lot of people died because of tsunamis and all that, and entire villages in Indonesia right now, like back in the day, like I think Dutch Indies or whatever, like were completely wiped out, and it was in August of 1883. So how come they reported that in September? Well, the answer lies with something called what is it called? I forgot. Easterly winds, which now we call the jet stream. So when like they didn't even know about it until like the Western like meteorologists, they didn't even know about this until Krakatoa happened, and the aerosol cloud, like it traveled like from east to west, so it traveled there like that outside the screen or whatever, and then it came back. So Vietnam, even though Vietnam is right there, like and Krakatoa is right there, the cloud didn't reach Vietnam until September, and we could actually like show this to be true because there were like some ships in the Philippines around there that reported like a blue sun or something in, I think in the 7th of September, so just 2 days before that. So the record, like the mention of the blue sun and all that actually helps like us like understand that yes, like the cloud like spread like that, and it confirms what we know basically. And so I want to end on that like volcanic / meteorological, because yes, these were like very important documents for like astronomy and all that, but they can also be useful to geology and meteorology because, like I said, these were like celestial records, not exclusively astronomical records. So yeah, they're very useful, and thanks for listening to me. And I will take some questions. Oh yeah. I don't have anything right now, sorry. I don't memorize what I write. Oh yeah?
When you're reading these medieval records, are you reading the original writing or are you reading like modern translations of what they wrote?
So it depends. Like the further back you go, like actually it's kind of interesting because the further back you go, the more understandable they are. Because like with the development of language, like the more modern ones, they have more like modern influence and all that from all the languages. But in the early days, like the Song Dynasty, for example, like the records are very clear because they try to stick to their original classical Chinese. So like if you were reading this, for example, like this line is like that's the name of the day, like sun color blue. So like day, sun color blue. So like that's easy to read, but if you like get into the nitty-gritty parts of it, it's like what are they saying? Are they like, is it like actually classical Chinese, or are they like influenced by something like their own language, something like that? Like they got sloppy with time. That's what I'm trying to say. Yeah, but yeah, like for example, like that's what it says. Like that's the name of the day, like Bing Tin something, and then sun color blue, and then that's something like travelers no shadow, and then like entire day no light. You see my pointer? It's pretty clear. Like yeah, and I also like studied a little bit of classical Chinese in undergrad. So anyway, yeah. Any more questions? Oh yeah.
So, when did a heliocentric version of the universe then, or the solar system, get accepted?
So it came with the missionaries in the like I would say like in the Ming Dynasty in the 7th century ish, 17th century, and also the missionaries didn't just go to China; they went to Vietnam, other countries. I think Vietnam and Korea were like more receptive of heliocentrism, like early on, and then China was like slowly like going to accept it and all that. There was some books by some like Vietnamese astronomers as early as like 16 something who was like, yeah, let me explain heliocentrism to y'all, something like that. So they, and for this, like for the purpose of this, like they were very like geocentric before the missionaries came, but they doesn't seem they don't think the Earth was flat, for example. They think it was like spherical and all that, but they think it was the center of the universe. So it's a very interesting like kind of like evolution, development. I don't really know what word to say, but yeah.
But there were no Chinese astronomers excommunicated for.
Oh no. They were arguing more about how to whether Christianity fits with Confucianism. Yeah, they weren't arguing about no. There was no Chinese or Korean Galileo. It was like yeah. Yeah. Oh yeah? What?
So you started by sharing the example of Hubble referring to the Chinese records, the Type 54 supernova.
Yeah.
Are there any other examples of kind of other scientists using the Chinese and Vietnamese records to support research like that?
Oh, there's a lot. Like something I forgot to I neglected to say here was that almost all of the supernova in the Milky Way that we know, except for the ones that Tycho Brahe and Kepler saw, we know they're supernovae because of Chinese and Japanese records. So like there's like if you ever went to the conference of the American Astronomical Society, there's a historical astronomy division, and they were talking about it. Like I attended their meeting in Seattle last year, and there was a guy explaining like some of the details of one of the Chinese records. Yeah, so they still talk about it to this day. Yeah, even last year. Yeah. Oh yeah.
So, when the Chinese unrecorded the supernova in 1054, what was their conception of the universe? What they were seeing? Were they just noting the fact, or did they place it in? What kind of universe did they place that event into?
Right. So the question. Oh wait, sorry. So the question is that when the Chinese and East Asian cultures in general were recording these events, were they just stating the facts, or how did they conceptualize the universe? Well, that's a good question actually, because like I said, they thought these things were like reflections of what's happening, like what might happen. For example, this blue sun right there, like after these lines, all of these lines, cause it was read from like left to right, right to left. So these parts were about the mandarins, the officials, seeing the blue sun, and they came to the emperor and were like, "Hey, guy, like you must be doing things wrong." And they actually like a lot of the responses were like politically motivated. So the emperor who was in power during this time, during the eruption of Krakatoa, he was pro-French. And he wanted he was very like he was not good at resisting French influence. So they used this blue sun to reprimand him, to be like, hey, heaven's telling you not to mess with the French. Like we need to prevent them from taking over the country and all that. So we don't like. It's kind of unclear whether they believe that to be true or they just use this like phenomena as like a political tool. Because a few months later, they killed the emperor. Yeah. So, yeah. Yeah. And any more questions? Like one more question. Oh, yeah.
Do you have a sense of when the corpus of East Asian astronomical data sort of arose to the West and sort of like came to the awareness of folks in the West, and when they started using those records as valid astronomical data?
Oh, that's a really good question. So the question asker, I don't know. The question is that like, how, like when did these like astronomical records like become like like valued by the West, and how when did they start to see it as like important like data? Well, so basically, a lot of the documents were also inside historical records. So like when people wanted to understand what history the Chinese and the Koreans and the Japanese and the Vietnamese had, they translated all of that. And some scholars in the around the like 18th century, by 18th and more like 19th century, began to notice like, wait, they got a lot of stuff about like comets and all that. We should look more into that. So if you took physics in high school, there was a guy named the Biot-Savart law. It's like some magnetic stuff. I don't really care. But but the Bio guy in that Biot-Savart law, he was the guy. He and his son translated some of the classical Chinese texts into French, and that's how Hubble became aware of them. He didn't read Chinese. He read French. Yeah, Hubble also fought in World War I, so he probably knew French. But anyway, so the interest started to be present in the late 19th and early 20th century, and then in the 50s and something like that, like people start to notice more and more. And when I think the peak was actually like in the 70s and 80s, something like that, when NASA scientists were like, we should look even more into this. And the Chandra X-ray Observatory, it actually like pointed at some of the supernova like candidates that the Chinese records like suspected, pointed to, and found some new things. So like I would say it began like pretty recently, like history-wise, 20th century-ish, and then now we're getting more and more invested in them. I hope that's an extensive answer. Yeah, but that's all the questions I can take. I can ask you, like you can ask me later. But, yeah. Oh no, it's fine. It was funny. I made a joke out of it. So.
Yeah.
Wait, how do? Oh.
Thank you. Okay, I'll just hold this here. Okay, let's give another big round of applause to both of our speakers this evening. I think another fantastic astronomy on tap. So with that, I just want to remind everyone that our next Astronomy on Tap will be on February 28th. So that is, once again, the last Wednesday of February. And stay tuned for details on that on our social media. I am planning something kind of out of the ordinary for that, more of a question panel. So look out for that and come with questions. And otherwise, I'm going to say get home safe, and thank you so much for coming. And if you won trivia, come get your prize.